Hello, this is lecture 25. This starts a series of lectures, 5 or 6, I'm not sure exactly how many, in which we will talk about movement of things across membranes. Now we just finished talking about receptor-mediated endocytosis. That's obviously a way to move something across a membrane. But in that case, you're using a vesicle to move and a receptor to move a large molecule such as an LDL particle or something like that across the membrane. So in this case, we're going to be talking about smaller molecules and molecules that may or may not be able to diffuse across the membrane. But in general, we're not talking about vesicles at all. We're talking about direct movement across the membrane. And we're going to see how the cell facilitates that movement, what the mechanism is, why it does it this way, and also what the consequences of doing it this way are. So let's begin by thinking about the kinds of molecules that would move across the membrane. We've got several listed over here on the right, and we've got a little table up here, or not a table, but a list up here with some general things to consider. So we're talking about gases, for example, carbon dioxide and oxygen are examples. We're talking about metabolites, maybe intermediates in a metabolic pathway that need to cross a membrane. In some cases, those metabolites may need to gain entry into a compartment, and in some cases, those metabolites may need to be retained in a compartment. So they may be generated in a compartment and you don't want them to cross a membrane. So when we talk about movement across a membrane, we're not only talking about facilitating movement, we're talking about mechanisms that will restrict movement. So we're talking here about selective movement of things across membranes. Also, during metabolic pathways, some waste compounds may be generated, and we may need to move those waste compounds across the membrane. So it could be any number of things, and we'll look at several examples as we go through this series of lectures. Now, if you look over here at this diagram right here, you can see that we've got a permeability scale. So on this axis, we've got the permeability coefficient, and notice that centimeters per second. So that's obviously a rate at which something is moving across the membrane. So something that has a high rate of movement has a high rate of movement because the membrane is permeable to that molecule, whatever it may be. So for example, oxygen can move across the membrane at a high rate because the membrane is highly permeable to oxygen. If we go down to the bottom and look, let's just say, for example, at sodium and potassium, we can see that the rate at which it moves across the membrane is slow. Now, in this case, we're not talking about mechanisms that get things across the membrane. We're just saying, in general, if movement relied simply on diffusion across the membrane, for something like sodium and potassium, it would be very slow. So what are the characteristics that determine whether or not the membrane is highly permeable or has a low permeability for a molecule? Well, there are two key things. One is size, and one is polarity. And so if we go over here to the left, you can see that hydrophobic molecules can move across the membrane at the greatest rate. That's why we've got a green and a relatively thick arrow. So what are these going to be? These are going to be molecules that are just simply very hydrophobic. In other words, their ability to diffuse through the inner part of the membrane where you have all those nonpolar fatty acyl chains is high. In other words, it's energetically feasible for them to pass through that compartment. Now, what about molecules that are not hydrophobic? What if they're polar? Well, if they're polar, then whether or not they're going to move across the membrane, whether they move across the membrane, is going to be influenced by their size. So if we look here in the second category, we've got some molecules that are polar. Water, for example, we know that water is polar. We've talked about that. We have urea, we have glycerol as examples. These are polar molecules, but they're small enough that they can still diffuse across the membrane. Now, if you just compare urea and glycerol right here, two examples from this category, you'll notice that their permeability coefficient is way lower than we had up here for oxygen. Also notice that it's considerably lower actually than water as well. So even though these are all polar molecules, all three of those, you can see that the difference in their permeability is determined by size. Now, but in general, we can put all those into a category that we'll call small and uncharged. Polar, but uncharged. The next category would be polar molecules that are large. So glucose is an example of this. We'll talk a lot about glucose. So we can see glucose right here. Its permeability is much lower. And then we get all the way down to the bottom, and these are things that cannot move across the membrane. Now, if you look at these, you'll notice that some of these things, like your hydrogen atom right there, all these ions are small. But the reason these things can't move across the membrane is because of their charge. Notice all of these are charged. So if it's charged, it's not going to move across the membrane. In other words, these are also polar molecules, but these are polar molecules with a frank charge on them, as opposed to those middle two categories where they're polar, but they don't have a charge. If you go over here to the right and look at this, you can also see how size affects this. But it's not just size that affects this, it's also polarity, because if you look at oxygen right here, notice that it's 32 Daltons, larger than water, but it has a higher permeability coefficient. And of course, again, we've said this, but the reason for that is because it's nonpolar and water is polar. So I think we've made the point there enough. It's polarity and its size. Now, if something cannot get across the membrane by diffusion, the question is, how does it get across the membrane? And the answer is that there are going to be proteins embedded in the membrane, let's say the plasma membrane, that are going to facilitate that movement. They're going to allow that molecule to get across the membrane. So in this cartoon over here on the left, we've got all these molecules on the outside and the purple triangles on the inside, and none of them are crossing the membrane. On the right, we've got some transporters. Some transporters are moving things in one direction. For example, this transporter is moving the purple triangle outside the cell. This transporter is moving the green rectangle inside the cell. And this transporter is actually moving the blue circles in both directions. And that's what we're going to see. We're going to see transporters that are involved in import, transporters involved in export, and transporters that can move things in both directions, oftentimes simultaneously. So it's these proteins we're really going to focus on for the bulk of this section. Now, toward the end of this section, we will look at how a lot of these proteins work together. And that's what this slide illustrates. That in order for a cell to maintain homeostasis, you're going to have these transporters working all at the same time. You may have, for example, a sodium transporter working on the plasma membrane, pyruvate, moving pyruvate across the intermitochondrial membrane. We're bringing glucose in, perhaps to use that as a source of energy. We're moving protons across the lysosomal membrane so we can acidify that compartment. We're going to end up looking at how these transporters work by themselves so that we can understand how they work. But we're actually going to, at the end, kind of come back and put all this together and see how they work together. Because if you move one thing across a membrane, you're going to affect the environment in both compartments, the compartment from which it came and the compartment to which it's going. And that the change in that compartment is going to affect the movement of other things. Now, lots of words on this slide. We talked about this a little bit earlier this semester, at least some of this, but we really need to dive into this a little bit more in order for this movement across the membrane to make sense. So we need to think about free energy and entropy and enthalpy and things like that. So, because what we're going to be doing, a lot of what we're going to be doing is going to involve calculating the change in free energy that occurs when something moves across the membrane. So let's talk about what free energy is. Free energy is a measure of the potential energy of a system. It's a function of both enthalpy and entropy. So let's define those two terms. Entropy is defined as a measure of the degree of disorder or randomness in a system. The higher the entropy, the greater the disorder. Now, I believe we talked about this early on in the semester when we were talking about protein folding, and we were talking about entropy. But another way that I like to think about entropy is entropy is a measure of the number of spaces that a molecule could occupy. And the analogy that I always think of is these classrooms that we're in have these square tiles on the floor that are about a foot square. So if you counted the number of squares in here, you would, and let's just say you could get a person per square. I know you can't, but let's just say that you could. Then we could say that we've got so many squares in here. Let's say this is a 300 square foot room. So we could get 300 bodies in here, one on each square. Now, if we had one person on each square, there would be no disorder. In other words, it would be highly ordered in here. There would be no room or no ability for a person to move from one square to another because the squares all around that particular person would be occupied. But let's imagine that in a 300 square foot room, in other words, a room with a potential for holding 300 people, we only had 3 people in that room. Well, what does that mean? Well, one thing it means is we could get a lot more people in there, but the other thing that it means, which is relevant here, is that those 3 people could move all around that room. In other words, there's so much available space, so many spaces for them to occupy that they could move. Their movement would not be restricted. In other words, they would not be ordered. There would be a high degree of disorder as random motion occurred as those 3 molecules were moving all around. So if you've got a low concentration in a space, then we're going to have a high degree of randomness or disorder, plus we have more potential spaces that could be occupied. So again, entropy is a measure of the degree of disorder or randomness in a system. The higher the entropy, the greater the disorder, the more empty spaces there are. Entropy is called S, by the way, because the person who really kind of defined this concept was a French scientist named Sadi Carnot. So S stands for Sadi. Now let's think about enthalpy. Enthalpy in a chemical reaction refers to the total bond energy. So the enthalpy of the reactants or products is equal to their total bond energies. So whenever we talk about a molecule and we talk about the energy in that molecule, we're really talking about the energy that's stored in the covalent bonds that link the atoms together. So when we talk about free energy, then what we're saying is the potential energy of a system, the free energy, is a function of these 2 terms. It's a function of both the enthalpy and the entropy. Now, we're talking about things moving across a membrane. This is a cell biology class in which we're interested in things getting from one side of a membrane to another. So of those two terms, entropy and enthalpy, which one do you think is the most important? Well, it's going to be entropy, because we're not really making and breaking bonds here. We're not changing the amount of energy that's contained within a molecule. So for example, if we move glucose across the membrane, we are going to affect the entropy because we're going to change the concentration on both sides of the membrane, but we're really not affecting the enthalpy because we haven't either created or destroyed any covalent bonds that link those atoms together. So we're going to see that when we move things across the membrane, the focus will be on entropy. So the change in free energy reflects the degree to which a reaction creates a more disordered state of the universe or a more probable state of the universe. Okay, so delta G, the change in free energy, is equal to the change in enthalpy minus the temperature times the change in entropy. Now we'll spend a lot of time talking about that, but notice that the change in free energy, the potential energy of a system, is reflected by changes in both the enthalpy and the entropy. And again, it reflects the degree to which a reaction creates a more disordered state of the universe. The second law of thermodynamics says that things tend to, closed systems tend to move in such a way that disorder increases. In other words, the change in a system, the spontaneous change in a system that leads to disorder is favored. Okay? Now, let's look at Gibbs' law. Gibbs' law says all systems change in such a way that free energy is minimized. Now that's perfectly consistent with the second law of thermodynamics, because if free energy is minimized, it's minimized because the order in the system has decreased, or the bond energies in the system has decreased. So when we calculate delta G, we're calculating a change in free energy. And what we expect is that if the change in free energy decreases or is minimized, that's going to be a spontaneous reaction. Because Gibbs' law is perfectly consistent with the second law of thermodynamics, which says under normal conditions, that's what's going to happen to a system. That's just spontaneously what happens to systems. Things go to a state of disorder instead of a state of order. And consequently, free energy is minimized. So to minimize free energy would mean that free energy is going to be negative. We're reducing the free energy. So if you calculate delta G and it's negative for a reaction, then the forward reaction will occur spontaneously. In other words, if we're trying to calculate the delta G associated with movement of a molecule across the membrane, and when we calculate the delta G, we find that the delta G is negative, then that means the movement across the membrane will be spontaneous. And we can rest assured that that movement across the membrane is going to be associated with an increase in disorder. On the other hand, if delta G is positive, then the forward reaction will only occur with an input of energy. Once again, if we're trying to calculate whether or not something is going to move from one side of a membrane to another, and we calculate the delta G and we find that the delta G is positive, then that means that's not a spontaneous reaction. It's not energetically favorable for that reaction to take place, and the only way that reaction is going to take place is if you provide a source of energy. Now, if delta G is 0, then that means the forward and reverse reactions are occurring at equal rates. The reaction is at equilibrium. So once again, if we're talking about moving something across the membrane and the delta G is 0, then it could mean that that molecule is moving across the membrane, let's say from the outside to the inside, but it's moving from the inside to the outside at an equal rate. So it doesn't mean that movement isn't occurring, it means there's no net movement. So calculating delta G is going to be really important here. We will calculate delta G a lot. And once again, we'll see that delta G is the key to this whole thing. It is a change in the potential energy of a system. Now, let's think about types of transport. By the way, we'll revisit this issue of delta G and entropy a lot. So if what we described on the previous slide didn't make a lot of sense, then just stay with me for a few minutes and we'll illustrate it in some ways that hopefully will make sense. So when we think about movement across the membrane, we can say that movement is going to occur by simple diffusion or protein-mediated transport. Those are your only two possibilities. So simple diffusion is non-protein mediated. Okay, so we've really got protein mediated and non-protein mediated. Now, if it's protein mediated, it can be either passive or active. If it's passive, it does not require an input of energy. If it's active, it requires an input of energy. So we'll distinguish between those two. So let's think in general here about the energy requirements for moving something across the membrane. The concept here is really simple. A molecule will move across the membrane if it's energetically favorable. Now, when we say that something is energetically favorable, what do we mean? Well, we mean that it adheres to the second law of thermodynamics, which means that things move in a state of disorder. That's the way they move. If things are in a state of disorder, then the potential energy has been decreased. And we said delta G is a measure of the potential energy. So what that means is that the delta G is going to be negative for that reaction. It's going to be minimized, as we said, according to Gibbs' law. If it is not energetically favorable for a molecule to move across the membrane, then will it ever move across the membrane? Not unless you give it some energy. But if you give it the right amount of energy, we can get that molecule to move across the membrane. So the bottom line is a molecule will cross a membrane if it's energetically favorable. If it's not energetically favorable, you can only get it across the membrane with an input of energy. Now this kind of describes this in kind of a cartoon form here. Notice that what we've got over here is simple diffusion. No protein is required. No protein required here. And all the other three here require a protein. And again, we've got passive transport here. And we've got active transport. The passive transport does not require an input of energy. The active transport does. Now, let's think about concentration gradients and the effect of concentration gradients on this. What this is showing is we've got a high concentration over here, and we've got a low concentration over here. Okay? Now, this is telling us that things tend to move down their concentration gradient. So if they move down their concentration gradient, then what does that tell us? Well, they could move down their concentration gradient without a protein. That would be called simple diffusion. And that's going to be things with a high permeability coefficient. So that's going to be things like oxygen, things like that. But what if it's got a low permeability coefficient? Now, a low permeability coefficient just simply means that it can't diffuse across the membrane because its permeability coefficient is so low. In other words, it's not soluble in that membrane. But the concentration gradient would favor movement across that membrane. So if we had a protein that could get it across the membrane, we could do it without a source of energy. So both the red ball here and the yellow ball are moving down their concentration gradient, but they need a protein to get them across the membrane. So that's going to be an example of passive transport. In this case, we're trying to move something against its concentration gradient, and that's going to require an input of energy. Now again, why does it require an input of energy to move something against this concentration gradient? Well, because it's not energetically favorable. Why isn't it energetically favorable? It's not energetically favorable because entropy in this case is, what's happening to entropy? Entropy is decreasing. Okay? In other words, what would happen is we would be going to a state of increased order. And we just said that systems are going, left to their own devices, systems are going to spontaneously move. Things are going to move in a system spontaneously in such a way that disorder increases. But in this case, order is increasing. So that's not energetically favorable. Another way I like to think about this is things move down their concentration gradient because in the area where there's low concentration, what does that mean? It means there are more potential spaces for the molecule to occupy. If you have a high concentration, there are few potential spaces for the molecule to occupy. That's why I kind of like to think of entropy in terms of available spaces to occupy rather than order or disorder, although they both fit. So let's think about simple diffusion. We could define simple diffusion or look at the characteristics of simple diffusion and we would say there's no expenditure of energy. That's what we just saw. Things are moving down its concentration gradient. So things are moving down its concentration gradient. So what's happening to delta S in this case? Let's look at our formula. We've got it here on the bottom, but let's draw it up here. Delta G equals delta H minus the temperature times delta S. Now we said there's no expenditure of energy. Things are moving down its concentration gradient. So what does that tell us automatically? It tells us automatically that delta G is going to be a negative, okay? Because we said a couple of slides ago that spontaneous movement occurs because delta G is negative. Now, how do you get a negative out of this? Well, are we changing bond energies? No. So delta H is 0. We're not going to worry about temperature here. All we're going to worry about in this case is our sign. So what's happening to entropy here? Remember, delta S is change in entropy. So entropy is going up. So entropy is a positive number. So 0 minus a positive number equals a negative number. And that's exactly what we've got here. So we can say that if delta S is positive, then delta G is going to be negative. Again, we're assuming no changes in bond energy. So that's exactly what you get with simple diffusion. It is energetically favorable. We know that because delta G is negative. And it's energetically favorable because there's an increase in entropy. Now, let's kind of think about why that is. The increase in delta S, or the increase in entropy, or the randomness or disorder occurs because there's less tight packing and therefore more randomness. In other words, if you consider something tightly packed over here, a high concentration over here, and we're moving it in here where there isn't much, then what's going to happen? We're going to see a big change in the packing here. We're going to get less tight packing over here. Now I know that you're going to say, well, but the more molecules you put in here, the more tight packing you're going to get. And eventually that's going to be true. Eventually you're going to get so many molecules in there that the packing over there is as tight as it is in the compartment where you started. But at least initially, that's not going to be an issue. And again, because that entropy increases, we'll have a decrease in the delta G. Okay, so again, just to summarize, we're going to move things down its concentration gradient, which is going to result in, or let me say this another way, as things move across the membrane, if they move down their concentration gradient, that's going to be reflected by a positive delta S and an overall negative delta G. Now, what do we have to consider then when we think about something moving across the membrane? We have to consider, by simple diffusion, we have to consider its permeability in the membrane, and that number is going to be called its partition coefficient. So let's illustrate this by looking at two molecules. Here's diethylurea and urea. Doesn't really matter what those molecules are, but what we notice is that diethylurea has a partition coefficient of 0.01 and urea has a partition coefficient of 0.0002. Now remember, partition coefficient is a measure of the permeability. Another way to say that is it's a measure of the substance's solubility in lipid. The more soluble it is in lipid, the higher its permeability rate is going to be. Now the math on this is really simple because all we have to do is say diethylurea is 50 times more soluble in lipid than urea, and therefore will pass through the membrane 50 times faster. Okay, so if you compare two molecules and you look at the rate at which they move across the membrane, now we're talking just simple diffusion here, we can see that that movement by simple diffusion is going to be reflected in the relative rate at which the two molecules move. Now, if we were to plot simple diffusion, in other words, we're going to look at the green line here. So let me just kind of draw this out, and we're going to say, okay, we're going to look at the rate of transport. That's going to be on our y-axis. Down here, we're going to look at the concentration of this transported molecule. And we're going to see that the rate at which transport occurs is a function of the concentration, and it's perfectly linear. In other words, if you had a compartment, if we had a cell, for example, and we're going to try to move things from, let's move this green molecule from, no, let's not use green. Let's use this purple. We're going to move the purple molecule across the membrane. It's saying that the higher your concentration of purple molecule, the greater the rate of movement. Okay? So what do we know about simple diffusion then? We can say that the rate is linear. We can say that the partition coefficient really determines the rate. We saw that on the previous slide. The higher the partition coefficient, the more soluble it is in lipid, the faster it can move across the membrane. Also notice there's no theoretical maximum here. Hypothetically, this is just going to keep on going. Okay? What that tells you is that the rate of movement is a function of what? It's a function of the concentration and the partition coefficient. It's that simple. The rate is dependent on the concentration of the ligand. That's what we know. Now, let's say that we do the same sort of experiment with another molecule, and we get something that looks like that. What's the difference between those two molecules? Well, the rate is linear, which means they're both molecules are moving across by simple diffusion. So the mechanism is the same, but at any given concentration, what we notice is that the red molecule is moving at a higher rate than the yellow molecule. That would be because the red one has a high, relatively speaking, a high partition coefficient. The yellow one has a low partition coefficient. Even though it has a low partition coefficient, it's still moving across the membrane by simple diffusion. It's just at a low rate. So let's think about something that's has a really low partition coefficient. Could you get movement across the membrane in a linear fashion? Yes, but whoops. Your curve may be way down here like this. In other words, you may not get any movement across that membrane until your concentration gets really high. Now, let's switch from simple diffusion and think about passive transport. We'll get to active transport a little bit later on. So we're still talking about moving something down its concentration gradient in the case of passive transport. It's just that the partition coefficient is so low that you have to have some sort of protein to facilitate movement. So that's what we'll look at now. Now, let's say that we're doing this and we wanted to graph this out. If we graphed this, it would be that red line there. So that graph looks like this. Now let's think about what that means. The first thing that you notice is that the rate is typically greater than simple diffusion. Now you may say, I thought the rate depended on the partition coefficient, but now we've got a molecule with a really low partition coefficient, but because it doesn't have to be solubilized in the membrane, it turns out that its rate can now even be greater than simple diffusion because it's not trying at all to be solubilized, or it's not necessary that it's solubilized in the membrane. So if you pick any concentration here, let's say this concentration, we would see that the rate is greater than simple diffusion. The partition coefficient is irrelevant. Now this is a little bit difficult because the partition coefficient is absolutely relevant in the sense that it's so low that we can't get diffusion. But what we can say is that if the partition coefficient is so low that you can't get movement by diffusion and you have to start using a transporter, then once you start using the transporter, the partition coefficient becomes irrelevant because the molecule's ability to dissolve in the membrane doesn't really matter anymore because it's moving by this protein-mediated process. The rate is not linear here. There's a maximum rate, and that's due to a limited number of transporters. In other words, if you're moving something across a membrane and you rely on a transporter to move that molecule across the membrane, once those transporters are saturated, you can't move things anymore. You can't increase the rate. So if you've got 1,000 transporters on the surface of the cell and they're all moving something across the membrane as fast as they can, then you can increase the concentration all you want to, but you're not going to increase the rate of transport. So there's a maximum rate. That maximum rate is referred to as the Vmax. Let's get rid of this. That's the maximum velocity. And again, that's due to the fact that you've got a limited number of transporters. Now the other thing here is that transport is specific. What does that mean? Well, it means if you've got a transporter that's responsible for moving a molecule across the membrane, typically that transporter is going to move just that molecule. It's not going to move a bunch of other molecules. And we'll talk about that a little bit later on. The rate at which it moves is dependent on the affinity of the transporter for the ligand. I'm going to come back to that one. The rate is dependent on the concentration. So you can see there is a concentration dependent effect. The higher your concentration here, the greater the rate, until of course you reach the Vmax, and then you can't increase the rate anymore. Now, we got to go back and focus on this one because this one is going to be really important. The rate is dependent on the affinity that the transporter has for the ligand. Now, we've already talked a little bit about affinity this semester, but let's remind ourselves of what affinity is. Affinity really is the ratio of the on rate to the off rate. We're not talking about attraction here. We're talking about affinity. We're not talking about an electrostatic attraction in which one molecule is drawn to another molecule by some attractive force. We're talking about the tendency of a molecule to bind to the transporter, in this case, based on the non-covalent interactions that exist between that transporter and the molecule. So, affinity is going to be really important. If, for example, you have a transporter that has a really low affinity for a molecule, it's not going to be able to transport that molecule at a very high rate. If there's a cell, and we've got a transporter right here that's moving this molecule across, but if it has a really low affinity for that molecule, then if the molecule binds but quickly comes off, then we're not going to get much transport. In other words, that molecule is going to have to bind, and it's going to have to stay bound long enough to be able to be transported across the membrane. Now, how do we measure affinity? Excuse me, I'm about to sneeze. Sorry about that. I took my headset off. I hope the sneeze wasn't too loud. Okay. The affinity is the concentration at which you get half maximal transport. Now let's think about that for just a second. If you're measuring the rate at which a molecule moves across the membrane, and that molecule has a high affinity for that transporter, then what that means is you don't have to have a very high concentration before you can move the molecule across the membrane. Because when the molecule, let's say we're moving it from the outside of the cell to the inside of the cell, we're moving it, well, let's move our yellow molecule here. We're going to move our yellow molecule from the outside of the cell to the inside of the cell. Okay, if your transporter is sitting there and it has a high affinity for that molecule, then it can bind that molecule and move it across the membrane. If it can't bind to that molecule, then it's not going to be a very effective transporter. Now, if you put enough of these molecules out there, if you get the concentration high enough out here, then every once in a while, one of these is going to bind and be transported inside the cell. So the concentration required to move the molecule into the cell at half of the maximal rate of transport is referred to as the Km. Now, this can become confusing sometimes because if you look at the relationship between Km and concentration, Km and affinity, is what I mean to say, you'll notice that they move in opposite directions. In other words, a transporter with a low affinity for a molecule, you're going to have a high Km, a high concentration. A high affinity transporter is going to have a low Km. Okay? So that Km, the affinity that that transporter has for that molecule, is going to play a key role in thinking about how these protein-mediated transporters work. So the question I've got down here at the bottom is, what happens to Km as affinity increases? Well, based on what we just said right here, we can see that as affinity increases, the Km decreases. Now, what we're going to do next is begin to look at some of these transporters and the way they work. Now, we're going to look at passive transport first, and we're going to start out by looking at what your textbook calls transporter mediated. I've never really liked that because, well, when I think of all of these as transporters, all the proteins as transporters, but your book is specifically referring to a specific type of passive transport. Now remember, this is passive transport. Why? No energy input required. Why? Because we're moving things down their concentration gradient. Why, if you're moving things down their concentration gradient, do you not have to have an input of energy? Because the delta G is negative. If the delta G is negative, it means, I'm just reviewing here, it means the reaction is spontaneous, which means it doesn't require an input of energy. And why is the delta G negative in this case? It's because delta G equals the change in enthalpy minus the temperature times the delta S, and we know that delta S in this case is going to be positive. We know that this is going to be negative, which means our delta H is 0, which means our delta G is negative. Okay, so I'm just saying that for review. Now with all that, to finish reviewing here for just a second, so the obvious question would be, well then why do you need a transporter? Why do you need a transporter? Because it has a low Km. In other words, its partition coefficient is so low that it can't just diffuse across the membrane. If it could just diffuse across the membrane, we would be using this mechanism. So what do we got here? We've got molecules with a low Km that are trying to move down their concentration gradient. That's what we've got. And they're going to use a transporter. Now, in addition to transporters, there are also channel proteins, as you saw on that last slide. Channel proteins and transporters are going to work differently. A channel protein is going to work exactly like its name implies. We're going to have a channel created in the membrane, and the molecule here will just move through that channel. A transporter, on the other hand, is actually going to involve a conformational change in the protein. And that conformational change in the protein is going to be the key to moving that molecule from one side of the membrane to the other. Now, we're not even going to worry about ATP-powered pumps because we're really focused right now on things moving down their concentration gradient, which we just showed doesn't require an input of energy. So these transporters are exemplified by the glucose uniporter. Now, a uniporter just simply means that it's a transporter that transports one thing, uniporter. Now, those transporters could transport a lot of different things, but we're going to use glucose as an example here. So our red molecule here is glucose. Okay. So here's what's going to happen. We've got a transporter there that's going to bind glucose. Before we say that, let's just imagine, what do we know about glucose? Well, glucose has a low Km. That's why we need a transporter. Why does it have a low Km? Well, for one, it's polar. It doesn't have a charge, but it's polar. And secondly, it's much larger than something like oxygen or even water. So that's going to give it a low Km. In other words, its solubility in the membrane is low. That low solubility is going to force it to rely on a transporter. So here's the way the transporter is going to work. Glucose is going to bind to the binding site. Now, that glucose could bind and it could come off. Bind and come off. We've got on and off. That's what we've got when it comes to molecules binding to transporters. But it undergoes this conformational change, and this change in conformation occludes the binding site, which means the binding site, at least momentarily, is no longer exposed to either the inside or the outside of the cell. Then it undergoes a further conformational change in which that binding site is exposed to the inside of the cell. And our molecule can come off. Now, if there are glucose molecules inside the cell, they could come back on. So we'll draw a glucose molecule there that could come back on, just like we could draw one here that comes off. So what do we got here? We've got off and we've got on. We've got off and we've got on. Now you might say to yourself, how's this going to give us net glucose import? Well, we're going to get net glucose import because remember we have a concentration gradient. So the concentration on the outside is relatively high. So let's say we have a glucose molecule that binds and then comes off. Well, what's likely to happen? Another glucose molecule, because the concentration is high, is going to occupy that site. So in all likelihood, when this transporter undergoes a conformational change, the binding site will be occupied by a glucose molecule. And then when it opens up, where the binding site is exposed on the inside of the cell, that glucose molecule will come off. Now, it's possible that it would be reoccupied, but why is that unlikely? It's unlikely because the concentration is so low. And because the concentration is so low, you get net glucose import. Now there's a couple things to think about here. Does the affinity of the glucose binding site change? In other words, when transporters like this work, does it require a change in the affinity of the molecule for the binding site? Now you got to be really careful here because your tendency is to think that we've got high affinity over here where we bind it and we've got low affinity over here. And that would make sense, but that's not the way uniporters work. It turns out there's no change in affinity. Now think about that. The concentration gradient means that you don't need to have a change in affinity because the high concentration on this side, outside the membrane, as we said, is going to ensure that the binding site is occupied. The low concentration on the inside is going to assure that we get net release. Now here's the interesting thing though. If that's the way a uniporter works, what does it mean if the concentration inside the cell exceeds the concentration outside the cell? In other words, let's say that this uniporter is working and we build up a high concentration of glucose inside the cell. In fact, let's say our intracellular glucose concentration now is higher than our extracellular glucose concentration. Well, if everything we said is true, what does that mean? That means that when this uniporter goes back, notice these arrows are going in both directions. So this uniporter, once it goes to this conformation and drops the glucose off, it goes back. So it's really sitting there on the membrane rocking back and forth in which and the binding site is exposed to one side of the membrane, then the other, then the other, and then the other. Okay? If there's no change in affinity and the concentration gradient is switched so that the concentration gradient inside the cell or the concentration is now higher inside the cell than it is outside the cell, what's going to happen? In that case, you're going to get net efflux, or movement outside. So what does that tell you about uniporters? It tells you that uniporters don't move things in a particular direction. In other words, they don't move them from outside to inside. They move things down their concentration gradient. The glucose uniporter couldn't care whether it's moving glucose from the inside to the outside or not. Now, let me tell you what's really fascinating about this. This is really cool. I know all of you in here have had general biology, so I know you've seen glycolysis. So let's think about glycolysis. We're going to get a glucose molecule inside the cell. So here's, I should have drawn it down here. We're going to get our glucose molecule inside the cell. What's the first step in glycolysis? Glucose is converted to glucose 6-phosphate. In other words, we're going to put a glucose on, we're going to put a phosphate on carbon number 6 of that glucose molecule. Why does the cell do that? Well, it does it for a couple reasons. One reason is because it destabilizes that glucose molecule so that the next step in glycolysis can occur. But it does it for another reason as well. It turns out that glucose 6-phosphate has a lower affinity for the glucose uniporter. And because it has a lower affinity for the glucose uniporter, once those glucose molecules, let's say our glucose 6-phosphate, we'll now draw as purple, once that glucose 6-phosphate gets in the cell, its affinity for that uniporter is low, so its tendency to bind relative to the rate at which it comes off is less. So we don't have to have a change in the affinity of the uniporter. In this case, we've got a change in the molecule, and that's going to change the affinity that the molecule has for the transporter. Now let's look at these glucose uniporters in a little more detail. And let's think about how they function and what that function depends on. So if we want to think about how much of a particular molecule is moved, let's say from one side of the membrane to another, again we'll use glucose as an example, could be anything, then what's going to determine the rate of movement? Well, one, it's the number of receptors or transporters. Remember, your curve is going to look like this, right? This being the V max. That's the maximum rate of transport. And remember, we said that that's determined by the number of transporters. So the more transporters you have, the more glucose, in this case, you could get inside the cell. Now the affinity is also important, because if you've got a molecule with a high affinity, then that transporter can bind that molecule and transport it to the inside of the cell. If it doesn't have a high affinity, then it's going to bind and it's going to come back off. Now remember, even if the affinity is low, if the concentration is high enough, we can still get some import. But the affinity is going to determine the rate. The concentration is also important. That's going to have everything to do with the rate at which transport occurs. Now I said concentration outside the cell because in this case we're moving things from the outside to the inside. And the other thing we know about these glucose uniporters is that the partition coefficient is irrelevant. And again, it's irrelevant, as we already said, because the molecule is not soluble in the membrane, which means the only way it can get across is to use a transporter. And that, of course, means, as we said, that we can essentially ignore the partition coefficient. Now, two things we want to do to look at the value of a uniporter. Remember on one of the earlier slides, I said that uniporters or transporters were specific. Well, let's take a look at this. This is the Km that the GLUT1 uniporter has for glucose. Now, cells have different versions of the glucose uniporter. We've got GLUT1, GLUT2, things like that. Those are going to exist on different cell types in the body. We don't need to worry about that here. We're focused on GLUT1. That's all that means. Now notice that its Km for glucose is 1.5 millimolar. Its Km for mannose is 20 millimolar. Its Km for galactose is 30 millimolar. Now what does that mean? So for which of these sugars does it have the highest affinity? It has the highest affinity for glucose. Remember what we said earlier, a high affinity translates into a low Km. Remember, and a low affinity translates into a high Km. Okay? So what does that tell you? That tells you that the glucose uniporter is going to do a much better job at transporting glucose than it is at transporting mannose or galactose. Now here's a way to think about this. What would happen if the concentration of each one of these three sugars was 1.5 millimolar? In other words, let's make the concentration the same. But because the affinity for glucose is so much higher, it's going to transport glucose at a rate that's much higher than the rate at which it transports mannose or galactose. Now we can actually calculate the rate at which it transports a molecule by using this formula right here. The velocity at which it transports a molecule across the membrane is equal to the Vmax divided by 1 plus the affinity over the concentration. So in class, we'll actually do some of these calculations and we'll compare the rate at which these three sugars are taken into the cell, and we'll also compare the rate at which a single sugar is taken into the cell at different concentrations. So that concludes our general discussion of diffusion and uniporters.